Good morning, everyone. Welcome to the EasyPower webinar series. My name is Jim Chastain. I'm an applications engineer here at EasyPower. We try to produce this webinar series twice a month and often have included guest speakers as we do today. Welcome and appreciate your support of EasyPower. Before I introduce our guest speaker, we would like to run a couple poll questions just to kind of get the measure of the audience and see if we're targeting the right strata. So if you would please help participate by responding. There's no obligation, but it does help our speaker understand to focus his message. So if you would please, here's what we're looking at. The first question is, has your company completed an arc flash hazard assessment? So let's see how everybody responds. Clearly, there's no obligation, and this is strictly for informational purposes only. But this is a very popular topic, and I'd like to get as many responses as we could. Looks like we're about 2/3 of the way there. Let's give this another 10 seconds. All right. Appreciate your responses. Here's how folks weighed in on this. So it looks like we have people that know what they're talking about, which is a good place to start. Our second question is, when was the arc flash completed or updated? And you have a pretty broad selection here. I'm not sure if the attendance records for the webinars this summer have been very high. I'm assuming that some of that has to do with the fact that some of us are constrained to working from home. But in any case, we appreciate your attendance and participation in the webinar. And thank you again for supporting EasyPower. We got another 10 seconds on this question. All right. Good. And here, this is a little bit more evenly split. And then the last question is, which arc flash mitigation are you paying most attention to, or as far as a solution? So this is a little more broadly spread out, and it goes to the heart of what the topics will be today. So again, also want to make sure you're paying attention to the Tuesday webinars that we do every other week. And those are posted either in the newsletter or on the website. And those are more pertaining to the operations and use of the EasyPower tools. So for those of you that want to keep abreast of developments there, I invite you to join us on every other Tuesday. So it looks like we have a quorum here. Thank you very much. And here's how people weighed in on this. Thank you. Now, joining us today is Mr. Mark Pollock. He's the Global Product Manager for Littelfuse. And Mark, the podium is yours.
Well, thanks, Jim. Just give me 1 second here to share my screen.
Perfect.
So I think that should be coming through, I hope.
Looks good.
Perfect. Well, thanks very much. And thanks for the participation on those poll questions. That's interesting to see. I have a couple of statistics from some surveys we've done, and it seems to reflect similar numbers. I have one that I'll show in the slide deck a little bit later, and really a broad usage of all the different mitigation methods. So that That's interesting to see. Okay, so as Jim already introduced, my name is Mark Pollock, and I'm with Littelfuse in our technology lab in Canada. So I've been with Littelfuse over the last 14 years, worked through technical sales, global sales, business development roles. But apart from that, since the university days, I've been a member of the IEEE, working through different standards committees or conference committees or different local section executives. And but that is something I've found quite rewarding. So encourage everyone to, if you have interest, to reach out to your local IEEE. My background is, I have Bachelor of Science degrees in electrical engineering and computer science from the University of Saskatchewan, and registered professional engineer here in Saskatchewan in Canada. So thanks again for everybody to take the time to join us and then talk about this topic. And although I am up in Canada in the Great White North, just for everybody everywhere else, we did hit 95 degrees Fahrenheit yesterday. So we're also having a pretty good summer that way. So I'll start by just showing a quick graphic here. And, sometimes the attitude can be, that, safety, well, that's the responsibility of the safety committee or somebody else to tell me specifically what I have to do. And really, safety is, needs to be part of the organization. It's really everybody's responsibility. So it's, the electrician who's working around the panels, around the equipment, to the equipment designers, management, everybody, not just those responsible for policy, but everybody has a role to play in electrical safety. So first, you can go ahead and give yourselves a pat on the back for braving what might be COVID webinar overload and joining us today. So there's a few things I'd like to cover. And first, starting with the anatomy of an arc flash event. I'm sure most everybody is aware of an arc flash event, but I just want to align on some of the hazards, and then we can move into the hazard assessments and a couple brief standards references. One of the key standards in really understanding the risk is IEEE 1584, and we'll have a few points on that as it was given a fairly major overhaul with the 2018 release. And after that, we can circle back to some of the mitigating methods for dealing with that incident energy after it's been calculated. But we'd also like to add a little bit of a twist in terms of trying to put a little bit of an ROI on that. And, it's all a little bit subjective, but it at least might stir some good conversation or good questions. And, as talked about, there are different methods, different ways and products to do that mitigation. And as the poll question showed, it looks like there is broad usage of all the different ones outlined in NEC at least. So there's a lot of things to talk about. So let's get started. So first, when you break down an arc flash event, it's a release of energy through, typically insulating a conductor. In this case, we're talking about air, between two conductive elements. So really, what that means is that the electricity will, break down and pass through the air and create a rapid release of energy. So, when you look at what is happening, there is a release of light along with the heat and energy that's following. And this heat is very extreme. So the extreme temperatures you can see on those arc events can be, 20,000 degrees Celsius, which if you do the math, can be several times hotter than the actual surface of the sun. And with that heat, the copper bus bars and the other, materials goes through very rapid expansion. And, as it's moving from solid to vapor, and that itself creates the explosion. And then you have projectiles of, molten metal and other things that are flying. And one thing, that's maybe not always talked about when you're standing in front of that cabinet and an arc flash occurs, the first human reaction is to do an involuntarily to inhale. And when you do that, when you have those gases and the molten copper particles, that can do a lot of damage, to somebody who's standing there as well. So the pressure that you can get from that blast, as I mentioned with that rapid expansion, can be equivalent to a stick of dynamite. And the sound wave that's part of that as well can approach 130 decibels. So you can liken that to standing next to a jet engine while it's fully operating. And of course, there's also the cost of damages. So that can be total equipment destruction, production downtime, and even worse, if somebody's injured, there can be other costs associated with that in terms of wages, medical bills, lawsuits. But first and foremost, the injury to personnel is a very serious event. So it's important to look at what are the points that contribute to the severity of an arc flash or the incident energy itself. So this is just a brief overview, not really intending to get scientific. There's a lot of great papers out there. So if there's questions on that, I can certainly help point to some that I've read. But generally, when we're talking about the thermal energy, we talk about I squared T, something like a thermal capacity of a motor. But for incident energy, we need to review some of the other factors. And here it's shown as two bullets. First, looking at the arcing current, and then looking at the resulting incident energy. So we look at the arcing current. The available fault current is a major parameter in that discussion. So that's the current that can be produced by the transformer or generator. And the second point there is the bus gap, so the air gap between the phase conductors where the arc is occurring. So in general, a bigger gap will give you more impedance, which could mean less current, if all the other variables are constant. And IEEE 1584, the standard we'll talk about in a little bit, does have some guidelines for those bus gap distances, tables with default values. And the electrode configuration is also something that has a significant effect. So we'll review that as well. The system voltage as well obviously does have an impact. Sometimes it could be maybe assumed that a higher voltage is a higher risk, but that's not always the case. Low voltage systems do have higher fault current levels, so that could contribute to higher energy ratings. But of course, the higher current values could also engage overcurrent protection at different ranges. So that can also have an effect on the protection. When we look at the incident energy, we look at the arcing current that we just talked about, and now we add the time and the distance from the arc. So in the testing, the arcing duration, so that time, has approximately a linear relationship to the incident energy. So if we can react quicker, we can reduce the total amount of energy that's released from a fault. So when you look at these factors, how much control or influence do we have over, the voltage or the current or the arc gap if we're doing a retrofit? So those are things that there's not a lot of leeway with, and some of the factors, especially in the retrofit stage, time is one of the critical items to address. So moving on, we'll talk a little bit about arc flash hazard assessments. And so this is, I mentioned one data point we had from a survey ourselves that we found 66% of the respondents said their facility had conducted an arc flash assessment. And just I'll confirm now that yes, we did have more than 3 responses. So that's still a statistical valid number. And that's good to see that, but it really needs to be higher number. The hazard assessment, the arc flash hazard assessment, is really the first building block of understanding where the risks are, and then from that point you can move forward to try to mitigate those. So that really is a very key first building block. And we'll talk a little bit here, about the values that come out of your arc flash hazard assessment. But in our review, in our survey, we had about 3/4 of people mentioning that they did have equipment rated at 8 calories per centimeter squared or higher. And really, that's just a line you can draw in the sand of, that's showing that there's equipment with a little more significant risk, where there's maybe more activities that can be done to reduce that energy and keep it as safe as possible. So what is an arc flash hazard analysis? Now, it's taking various mathematical methods and using them to try to estimate the potential or the risk of injury that could occur if an arc did happen in that piece of equipment. And once you have that information, then we're trying to change our actions based on that. So once we identify that, what the overall mathematical analysis and the number, we can identify what is the actual exposure to a worker who might be standing in front of the equipment, who might be working with the equipment. And as we continue to drill down, we can then look at, well, what is the flash protection boundary? So that's the boundary where the energy would be down to 1.2 calories per centimeter squared, a distance where you can limit potential burns to to second-degree burns. So it's an area where you start to be concerned about the human effects from an arc. And if you continue to drill down, you get to the appropriate work distance. So then you look at the limited approach and the restricted approach boundaries that define what the risk is and what the distances are and where you need to get your personal protective equipment on. And finally, there, the calorie rating of the PPE. So once you have your hazard analysis complete, you can understand what type of PPE is required to provide that last line of defense in that situation with that equipment. So once you do the mathematical analysis, your arc flash hazard is expressed in the incident energy, and the units there, I've been talking about calories per centimeter squared. And your PPE, so your arc flash protective clothing, is also rated in calories per centimeter squared. That one is given a name that's shown on the screen there, the ATPV, the arc thermal protective value, performance value, sorry. And of course, you want to make sure that your PPE rating is sufficient to protect you from the actual arc flash incident energy rating from that particular piece of equipment. So when you look at how the standards and regulations tie into this, OSHA 1910 is where it gives the mandate or the requirement to employers to provide that assessment. So that clause is where the requirement is given to do that arc flash hazard analysis if there are hazards likely to be present. So the OSHA text doesn't go through and describe exactly how the calculation should be done, but it references the other standards that are put together to address that. So it references NEC, the electrical code, as well as NFPA 70E and IEEE. So NFPA 70E, the standard for electrical safety in the workplace, and the harmonized version of that in Canada, the CSA Z462 workplace electrical safety, those standards talk about how to provide electrical safety policies, procedures in the workplace. And those standards also talk about requiring an arc flash risk assessment to be performed and documented. And there are procedures outlined in those standards that go through how to do that, how to do risk assessments for arc flash, for shock protection, and also then links back with IEEE 1584. So finally, that is a specific guide for performing arc flash hazard calculations. So in that text, it provides the formulas and a lot of tables and correction factors that allow you to try to identify what the actual arc flash hazard and incident energy ratings are. So there's also software tools, of course, that are available to do that calculation. So they will base that off of the IEEE 1584 formulas. So that gives a little bit of a flavor of how those all link together. Now, when you look at the electrical codes that we have in Canada or US, so the National Electrical Code in the US or the Canadian Electrical Code in Canada, they are in place to provide a minimum bar for electrical installations and equipment to ensure safe operation. And those as well refer to the IEEE 1584 standard and the NFPA 70E CSA Z462 documents to design that electrical safety program and do those calculations. So the clauses I've put on the screen here really reference the requirements to have the labeling on the equipment. So it makes sure that you can warn people of what the potential arc flash hazards and risks are. And of course, it talks about the label needing to be clearly visible so that qualified people can use that information and safely interact with the equipment. And ultimately, that label that we're talking about, it also needs to show the appropriate information so that somebody can understand there is a risk associated with it and what to do with it. So that label that's on the left, while it does give a warning that there is an arc flash hazard, it doesn't give you the information needed to then come back and have a safe work practice or safe work procedure based on that information. So the label needs, of course, to show things like the voltage, the incident energy, the working distance, arc flash boundary, and those are defined by NFPA 70E. There's a clause shown on the screen. And again, a couple important items there are the limited approach boundary and the restricted approach boundary. So that limited approach is identifying that a shock hazard exists within that boundary and that non-qualified people should really stay back unless they have the appropriate PPE or are escorted by somebody. And the restricted approach is a higher level of risk where only qualified workers with training, with a work plan, potentially even an energized work permit, will enter that space to do the work. Okay, so moving on to the IEEE 1584 standard itself, I want to highlight a few of the changes. And again, this is certainly not a comprehensive review, but a few highlights that would be interesting. So with the 2018 version, the new data was based on a whole battery of additional testing that was done. So here shows over 1,800 tests that were performed, and the formulas apply to systems that are 208 volt up to 15 kV. And so there's three different equations provided by IEEE 1584, built at 600 volt, 2.7 kV, and 14.3. And then there's interpolation used to build the numbers for the other voltages. And there is a range of voltage fault currents that are now dependent on those voltages, as well as electrode gap values that are now also dependent on voltage. So there's tables provided in IEEE 1584 that give those ranges. And so those are now dependent on those on the voltage levels. One of the, I think, most significant changes is the different electrode configurations. So through the testing, depending how the electrodes were positioned, there can be 2 or 3 times the incident energy that's produced from the arc jets that come out of the bus when there is an arc across the bus. So that has a really significant impact. So in addition to the actual electrode positioning and configuration, there are enclosure correction factors that are also provided. So it really allows the formula to adjust the incident energy based on the enclosure opening. So the standard enclosure opening of 20 inch by 20 inch, and the maximum value provided is 49 inch by 49 inch. So the formula doesn't completely change based on the volume, but ultimately it reduces the incident energy for the larger openings as that energy is less tightly focused, coming out of a wider opening. And if it's a shallow enclosure, that trend is also reversed. Another point of interest, in the previous standard, there was an exemption, for less than 240 volts, less than 125 kVA, and that exemption has been removed and replaced with a statement that I've put in here, verbatim, that sustainable arcs are possible, but are less likely in three-phase systems operating at 240 volts nominal or less with an available short circuit current below 2000 amps. And another bullet point there, that system grounding is no longer considered as part of that. So there's no longer a penalty applied for an ungrounded system in that calculation. So looking at the actual electrode configurations here, as I mentioned, there were several that were tested. So this is the VCB, or vertical conductors in a box. So you can see the photo on the right, shows the conductors placed in a vertical fashion. And on the left-hand side, just shows, not really animation, but just a step through it quick. When the arc forms, the additional testing and research really showed how the arc came out of the ends of the bus bar and was directed in that way. So the arc jets that form on the ends of the bus bar really directed where that energy went. So you can see how that would have an effect on the energy if you're standing in front of the panel, that would affect the amount of energy that's coming towards you. So this shows how the energy is directed down away from that bus bar in that enclosure. So the next configuration, VCBB, has vertical conductors into a barrier in a box. And again, the photo example on the right, you can see the conductors terminated onto a piece of equipment. So it's terminated onto a barrier. They're not just open. And again, in an overall box, inside an overall enclosure. And in this case, when you have arcing occurring at that barrier, the energy cannot go into the barrier, so then it's reflected outwards off that barrier. So that again has an effect on what energy would be experienced by somebody who's standing in front. And the next configuration, HCB, which stands for the horizontal conductors in a box. And here you can see on the photo on the right, the fuse holder, has the clips that protrude out, basically facing right towards you. So this is, a common configuration for some of these boxes where you have, fuses. So you're commonly opening a little panel door and you might be looking right at this. So that in this configuration, when the arc forms on the end of the conductors, now the jets are pointed, the arc jets across those ends of the bus bar are pointed right directly towards you, or right directly out the front of that enclosure. And the size of the enclosure does have, the impact as well, which is why, there is a separate model here for horizontal conductors in a box. So it makes sense that the size of that box and we'll say the depth or the shallowness as well can affect how focused that energy is coming out of that box. And the next, the last two here, the VOA configuration, the vertical conductors in open air. The photo on the right shows, the bus bar in open air and how they're positioned downward, so in a vertical fashion there. And again, seeing what was on the last few slides, it's no surprise that the arc energy is directed down off the ends of those bus bar. Now, in this case, because it's open air, there's not an enclosure to direct that energy, but the arc will naturally extend out from the bus, and the energy is still focused downward, but the enclosure is not around it to further focus that energy. And finally, the HOA configuration, horizontal conductors in open air. Last but not least, and I say that on purpose because it certainly is not the least energy. In this model, again, you're looking directly at the ends of the bus bar. So when the arc forms across those across the bus, the arc jets will direct the energy straight outward. And if you're standing in front of that, of course, then that has a significant impact on directing all that energy towards you. So accommodating some of these different configurations was a pretty significant step in updating those formulas. Now, just to review the actual steps for the arc flash analysis. So the IEEE 1584 standard does have specific steps that it goes through. And just as a point of reference, this slide here is showing the 2002 steps. You first always start by collecting the system and the installation data. And for a lot of existing applications, that is going to be the bulk of the work, is to make sure that all the data is correct, that you have the accurate information from your existing equipment. And second, looking at the modes of operation. So here, this is deciding or understanding, do you have alternate or standby sources that need to be included? Do you have tiebreakers? Are they going to be open or closed? And whether motors are considered to be running or de-energized at the time of arc. So those are things that go into the mode of operation. And from there, you progress to do the bolted fault currents, the arc fault currents, look at the protective device characteristics that you have in the system, document the system voltages, and select the working distances, and finally the incident energy and the protection boundaries. So I go through those last points really quick because I want to highlight those more on this slide. So here, the 2018 version adds one more step. So it goes from 9-step to 10-step. And what I've highlighted in yellow is really what has changed. So the bolted fault currents, that's a short circuit current analysis, that might be done to IEEE 551 or another standard. The gap size, the gap and enclosure size listed there as step number 4. There are default values that are given in the standard for that. Step number 5, the electrode configuration. So we went through those different configurations. That is, important to make sure that the calculation will come out with the correct value. So that's something new to select. Then to determine the working distances, it's really the same as 2002 standard for the most part. There's a table with the defaults, but there's now a minimum 12-inch working distance. The calculation of the arc current, step number 7. This one is where the determination of your system modes comes into play. It's not always simple because you may have time varying sources, such as generators, or maybe limited time sources like induction motors that can feed back. And then number 8, looking at the arc duration. And number 9, the incident energy. And number 10, the flash protection boundary. So the flash protection boundary is still defined as that distance where the incident energy is 1.2 calories per centimeter squared. And overall, I guess as a note, this model is intended to be used by a qualified person who understands and can do the analysis. So it's just a point I want to add in there. Now, when you look at some of the changes. What effect does that have on the mitigation methods, or how you might choose to mitigate? First and foremost, that horizontal electrode configuration has a higher energy level, and so that can impact and make it more difficult to meet some of the performance requirements depending on what mitigation method you're choosing. It's also good to be aware that there is some higher arcing fault currents with the formulas, and that can change the profile of how your overcurrent protection devices will fit into the scheme and will coordinate. In some cases, it actually makes them provide better interrupting just because of the high current. And this table here is a little bit of an eye chart. So I'm not going to run through everything, but I want to just highlight two things in particular. So this was from a partner company that we're talking to, showing some examples of the actual difference in incident energy. So that's the far right-hand column of each section of the table, moving from 2002 to 2018 formulas. And the two things I want to mention, that strip of red in the middle, if you see that all of those are horizontal bus bar configurations. And in all of those cases, there was a significant increase in the amount of incident energy that the formulas produced. And so that's one of the factors. It's not the only factor, but that horizontal bus bar configuration would be one of the contributing factors. Now, if you also look at the blue rows, you can see that a lot of the vertical bus bar orientations, the energy in the calculations went down. So what was a more conservative calculation used for everything in the previous standard, the 2018 standard attempts to provide a little more accuracy based on the configuration and the other factors. So now let's continue the discussion and talk about some of the different solutions that are available to do the energy reduction and make a little bit of an attempt to look at the return on investment. So NEC Article 240.87, which we'll look at, there are 6 specific approved methods. So those are ones we can take a look at. And I have the slides showing up right here. So 240.87 has a requirement that's been in here for a few code cycles to have arc energy reduction whenever you have a circuit breaker that can be adjusted to 1200 amps or higher. And it's interesting to note it's not when it's set, but if it just can be set to 1200 amps or higher. In the NEC 2020, I've left the gray highlighting there to show what's new specifically in 2020, which is just a requirement for documentation to show that method you've chosen is actually providing the reduced clearing time and the energy reduction. So the specific items mentioned here, zone selective interlocking, differential relaying, energy reduced maintenance switching, active arc flash mitigation relays, or an instantaneous trip setting, or an instantaneous override. So those are specific items that are mentioned. And point C, Article 240.87C there, again, that was a new clause added, which is just adding, again, a requirement for documentation to show that you've tested it if the method you've chosen is possible to be tested with current injection. Something that was added in 2017 code cycle, if I'm not mistaken, was the requirement to do similar arc mitigation also on systems where there was fuses. So if you have a fused load break switch, when you're using fuses as your interruption method, there's the same requirement is now added in order to have supplementary or additional devices that are going to be providing some sort of arc mitigation. So here under 240.67b, the list is a little smaller, but it talks about differential relaying, energy reduced maintenance switches, energy reducing arc flash mitigation systems or relays, current limiting electronically actuated fuses, or an improved equivalent means by the AHJ. So this is something that has also been added so that the circuit breakers and the fusing were given the same treatment in terms of limiting arc mitigation. Now we'll try to assign, a very rough ROI on some of these. We'll talk about these individually, but I want to highlight the hierarchy of controls on the right-hand side as well. That's part of the NFPA 70E standard. So that hierarchy of controls talks about different ways you can put in controls in place. And as you get to the top of the pyramid, they become more effective. In some cases more difficult, but they become more effective. And so as I talked about assigning that ROI, trying to be trying to give everything an even rating as much as possible, but just looking at the comparison of one to the other. So we look at the cost of the design. You might have to have a coordination study that's being done, looking at the cost of the equipment itself, what new equipment might be required to put that method into place, as well as the cost of, the downtime, the length of time to install it. And of course, the ultimate goal is calorie reduction. So that's also something we need to take into account, is what benefits will come from that. So starting at the top of the pyramid with, the most effective types of controls with, so substitution here, reducing the available fault current by substituting, one large transformer for, two or more smaller transformers in branch circuits. So that would serve to limit the amount of short circuit current, or, that it could be available, amount of energy available on a particular branch. But when you make these kind of decisions, that can certainly impact the project, possibly to the tune of millions of dollars. So it's something that would need some engineering study, and of course would be very difficult to try to do this in a retrofit situation. So if we look at the cost of the design, typically we, relatively speaking, say it's high, as it would change fairly significantly the organization of the system. The cost of the equipment can also be quite significant, and the downtime, relatively speaking, could also be significant, as reworking that system architecture would have some downtime applications if it was in a retrofit situation. So the calorie reduction could be quite impactful if you were to follow through with this method. Another form of risk mitigation that is popular in some applications is arc-resistant switchgear. So this acts as a permanent layer of really effective PPE, as it contains and redirects that blast energy, up or out and away from the workers. So this can be vented outside, or just vented off to the side as well. So this type of gear does have a cost associated with it, of course, just based on the additional build that has to be done to accomplish that, as well as possibly some extra cost in retrofitting the building itself with the arc plenum. So the equipment damage will still be considerable, because the actual calorie reduction, there is no reduction inside the equipment itself. So the internals of the equipment could be significantly damaged, but you would have good protection to human life, somebody standing out front, as the equipment will contain that. Now, one thing to be considered is, if a door is open, during maintenance or some other event during an arc flash, then that additional protection is not really going to have an effect. It's going to be neutralized by the door being open. And so here, when we look at our boxes there, the cost of design can be relatively low. There's some things to take into consideration, but not overly onerous. The cost of the equipment, however, is fairly high, and the equipment itself, as well as any modifications potentially made to the building. The cost of the downtime is also fairly significant, as in, if there's an arc event, there would have to be, rebuilding of the equipment containing that gear, as it's not providing a calorie reduction to the incident energy. And so that's one of the reasons why this isn't mentioned as a 240.87 method, as it's not specifically reducing the calorie, the incident energy value. An engineering control that can be added is zone selective interlocking and bus differential protection. So these schemes both do a really good job of mitigating the arc flash risk, but the return on investment will probably depend on how complex the system is overall. So both of these options require engineering resources on the front end, ensuring that the breaker settings are configured. In a retrofit application, implementing these schemes may require the addition of CTs, potentially new breakers. So in particular, the addition of CTs can be a bit of a bear to deal with, depending on where you have to add those. If those CTs are already in place, of course, then that time is reduced. One more caveat to mention, with bus differential, it is something that could potentially interrupt the selective coordination that you might have built into your system. So if there is a flash, it could take down a little more of the equipment than was originally intended. So here we've listed the cost of design a little bit on the higher side because of the engineering requirements we're talking about to select the breaker settings and do that coordination in advance. The cost of the equipment itself, pegged in the medium level, as we're talking about potentially retrofitting, a number of breakers and adding current transformers if we're in a retrofit application. And the time frame to do that could be multiple days once you're trying to put that all into your system. And finally, under the calorie reduction, both of these methods are quite effective, so listed on the medium and high scale there. Another engineering control that is mentioned are using arc flash protection relays. So these relays use light as their detection, the main detection driver within the equipment. And if light is detected, then a trip signal would be sent to a shunt trip breaker, or if it's paired with a quenching device. But the detection with the light can happen very, very quickly. And industry standard values are less than 1 millisecond, which is almost instantaneous. So the arc flash relays tend to be a standalone piece of equipment, and the cost of design to put them into the equipment is generally fairly low. Once the study is conducted, adding the arc flash relay generally can be layered in on top with existing breakers, existing equipment, and take advantage of that calorie reduction. The cost of the equipment generally also fairly low, as the arc flash relays and sensors can be installed in the equipment and not need too many different components in most standard sizes of equipment. The cost of the downtime is usually on the lower side. Most installations don't take too long to layer in, but if you have more significant or more dense equipment with components, there is a possibility of taking a little bit longer to do that install. So have shown it as a low to medium cost for downtime. The arc flash relays do provide a very strong calorie reduction in terms of mitigation, so show that as a high calorie reduction as well. And for those that are not familiar, with the light sensors or how they work, there's two different types of sensors you can see on the market. There's both single point sensors, or there's fiber optic sensors. So that allows them to be installed, in many different kinds of cabinets, or the fiber optic sensor can be placed in bus bar chambers or other difficult cabinets where there's a lot of different pieces of equipment. So with a relatively low number of components, can provide arc detection in most types of equipment. And this shows how this would be configured, on a typical system. So like any type of other protection relaying system, it can be set up with multiple zones to work with a tiebreaker application, so that if an arc is seen on one side of the bus, the light sensors can detect, trip the local breaker or the feeder breaker for that side of the bus, as well as the tiebreaker, and allow the other side to continue operating. So one comment that is often mentioned for the arc flash relays or arc fault mitigation systems, as it's mentioned in the code, is that it can be difficult to align with some of the switchgear testing and to verify that it's correctly installed. And there's a few standards that are fairly recent on the market here that are working to address that. So I think it's worthy to mention as an update. So 60947-9-2 is a standard that's in development. So that is, we'll say, a product standard specifically on arc flash detection relays. So that will help provide some standardization for the industry. And the IEEE 63107, that technical specification with that image on the right, that is a standard that works to define how the product can be integrated. So it specifies tests to show that the device is correctly installed and correctly integrated with the equipment. And maintenance mode circuit breakers is also another a popular method. And so this would be more of an administrative control rather than an engineering control, as it does require human effort to turn the maintenance mode switch on and off at different timing. So the cost of design is fairly low. It often just requires upgrading the type of breaker that you may already have in place. The cost of the equipment will depend a little bit on the complexity of the system. If there are a lot of breakers that need to be updated, then they may all need to be upgraded at the same time. And so that might add to a little bit of the downtime and the amount of effort that's put into upgrading those in the cost. The calorie reduction is also fairly high. So that is something that, when this maintenance mode is switched on, it is quite effective in reducing the incident energy. But again, that one important caveat is that it does rely on human intervention for somebody to engage the maintenance mode switch. And finally, we talk about PPE a lot as a key part of this. And PPE alone is worthy of mentioning here, just as a conversation point, that it's not really an effective solution for mitigating arc flash hazards, as the only method. It's really, the last line of defense from arc energy. So with, the PPE, although, the cost can be reasonable and it's still something that needs to be in place for each of the employees to work on the equipment, it's not something that is really in place in the equipment to provide permanent, arc mitigation. And as it's shown here, there is no calorie reduction, as it's not reducing the energy. It's instead providing you with your last line of defense when you're working on the equipment if something were to go wrong. So showing a little bit of a summary here, a lot of the methods are pretty effective in providing calorie reduction or incident energy reduction, but some of them may end up incurring a little more cost of design or have a little bit higher price point on the equipment itself. But we should really strive to implement engineering controls as much as possible. So really working to try to stay to the top of that pyramid, things that do not require as much, rely on as much human intervention and get away from that human error. So in summary, we've covered quite a bit of ground here and gone over some things fairly quickly, but we've covered how arc flashes some of the effects of arc flash events, talked about arc flash assessments, and the need to be done by a qualified individual, and how that gives you the incident energy value for your equipment that can help identify what the next step should be to mitigate that. So hopefully those updates on IEEE 1584 were of interest, and gave some points to think about when you're looking at how to do the mitigation on your system. So that's all the content that I had here today. So that brings us to the end of the presentation. I know we're getting very close to the top of the hour again, but Jim, we probably have time for a question or two if some have come in.
Yeah, we have a number of questions, and unfortunately we are close to the time. So I guess the first question that came in from Omer is, does a similar standard exist in the IEC world as far as the compatibility with IEEE compliance?
My understanding, I guess, when you talk about a standard relative to the IEEE compliance, I'm not sure if that means relative to the local laws, like OSHA has, or if that's in terms of NFPA 70E. But I guess my experience is that NFPA 70E is referenced around the world as, as a very good document to design your electrical safety program. And I know there are several different, countries that are working on, similar versions to it. I'm not aware of a specific IEC standard that is an equivalent, but one may exist. I'm just not aware of it myself.
And the second question is from Nazarene: what standard for arc flash calculations is used as the basic guideline for complete analysis and calculation in Canada?
Well, in Canada, the Canadian Electrical Code and in particular the CSA Z462, that's the Canadian equivalent of the NFPA 70E, they both reference IEEE 1584 as a standard that can be used for a basis. So that's the one that I'm aware of that it references in terms of the arc flash calculations.
So we're right up next to the minute timer here is for the end of the questions. Did you see any on the list that you wanted to address, or do we want to pick up the rest via email? Here's a quick one that may be...
I'm just trying to...
Let me jump in. This is, how do you address single phase requirements for labeling? That's a ticklish question.
Well, that's a good question, and I will say that I would probably get somebody to help me with that answer, because I don't know that I have all the background to give a complete answer to that. So I can follow up with an answer by email with support of a colleague on that one.
All right, fair enough. Yeah, I think we need to close out the session. Mark, it was an excellent presentation. I really appreciate your support, and we look forward to the next time you're able to join us.
Oh, well, thank you very much. I appreciate everybody joining and taking some time.
Have a good day.